Hi, welcome to the series of video lectures on microwave engineering. Today in this session, we will discuss the applications of magic tea or hybrid tea. So this article comes in unit 5 of the subject microwave engineering. Let us see the first application of magic tea. So measurement of impedance. So that means this magic tea can be used for the measurement of unknown impedance. Let us see this arrangement. This arrangement can be used for the measurement of unknown impedance. Let us see what are all these connections in the coming sessions. A magic tea can be used in the form of a bridge for measuring unknown impedance as shown in the figure. So this magic tea is connected in the form of a bridge to measure this unknown impedance. The microwave source is connected in arm 3 H arm and null detector is connected in arm 4 E arm. The unknown impedance is connected in arm 2. A standard variable known impedance is connected in arm 1. Let us see this. This is a 4-port device. You can check that port 1, port 2, port 3 and port 4 of magic tea. The port 3 is connected to microwave source. What is this port 3? It's generally H arm. The null detector is connected to port 4. This is E arm of magic tea. The unknown impedance whose impedance we have to calculate or we have to know is connected to port 2, which is Z2 here. The standard variable known impedance where we can vary this impedance is connected as Z1 to port 1. So this is the first arrangement we have to do by connecting this like this to measure or to know the value of unknown impedance. From the properties of magic tea, the signal from the microwave source A3 gets divided equally between arms 1 and 2. So that is A3 by root 2 to standard variable impedance and unknown impedance. We can see this. What is this point is that this microwave source generates a signal which is called as A3 H arm. From the property of H arm, what it will do, from the property of H arm, this A3 will be divided equally. So when the input is given to H arm, it is equally divided between port 1 and port 2 of equal amplitude and in phase. No signal is travelled to port 4 or no output is obtained at port 4. So that means port 3 and port 4 are isolated ports. You can see this is the input from the microwave source. The microwave source, it is equally divided into two parts, A3 by root 2, A3 by root 2 because of H arm property. So these two are of equal magnitude and they are in phase. So that is what we are doing. We are giving a signal which is divided equally between port 1 and port 2 like this. Since these impedances are not equal to characteristic impedance Z0, there will be reflections from arms 1 and 2. You can see that. So since Z1 and Z2 are not properly matched, so that means they are not equal to characteristic impedance Z0. From the transmission lines theory, when the ports are not properly matched, then the reflections will occur. So therefore, the signal which is travelling towards Z1, A3 by root 2 gets reflected, and the signal travelling towards Z2, A3 by root 2 is reflected because Z1 and Z2 are not matched to the characteristic impedance Z0. Now, the signals A3 by root 2 into rho 1 and A3 by root 2 into rho 2 enter the magic tea junction from arms 1 and 2, where rho 1 and rho 2 are reflection coefficients of Z1 and Z2 respectively. What this point is that you can see this signal A3 by root 2 gets reflected because of mismatching. So therefore A3 by root 2 into rho 1, this is the signal which will arrive at the junction. This is the signal A3 by root 2 gets reflected from Z2 because this is not properly matched. So therefore A3 by root 2 into rho 2, where rho 1 is the reflection coefficient of Z1, rho 2 is the reflection coefficient of Z2. So therefore these signals, you can see that these signals coming to the junction travel towards null detector, further multiplied by 1 by root 2 and minus 1 by root 2 because when they enter into the E arm, so they are further divided by 1 by root 2 and 1 by root 2 because of the property of E arm, it gets minus sign here. So therefore this signal will be multiplied by 1 by root 2 and the signal when arriving at null detector will be multiplied by minus 1 by root 2 because minus is taken because of the E-arm property. So the resultant wave into the null detector, that is arm 4 E-arm, is given by the net wave reaching the null detector. So therefore, what is the resultant wave reaching the null detector? 1 by root 2 A3 by root 2 into rho 1 minus 1 by root 2 into A3 by root 2 into rho 2. So this is the resultant signal. So that is reaching to the null detector. So therefore, that is what we have written here. So that is, you can write A3 by 2 into rho 1 minus rho 2. For perfect balancing of the bridge, equate equation A to 0. So for perfect balancing of bridge, equate this term to 0. So A3 by root 2. So from this what we can get? Rho 1 minus rho 2 is equal to 0. Rho 1 is equal to rho 2. What is rho 1? Reflection coefficient, and rho 2 is reflection coefficient. What is the reflection coefficient rho 1? Z1 minus Z0 by Z1 plus Z0. This is the reflection coefficient formula. What is rho 2? Z2 minus Z0 by Z2 plus Z0. So this is the reflection coefficient formula from transmission lines. So by observing this left side term and right side term, you can make the assessment that Z1 is equal to Z2. So that means what you can see, that when Z1 is equal to Z2, you can see from this diagram, when Z1 is equal to Z2, the bridge gets balanced. That means the null detector shows 0 reading. So this is a very important point. If Z1 is equal to Z2, then the bridge gets balanced. So this is a very important point. When Z1 is equal to Z2, the bridge gets balanced and the null detector shows 0 reading. Thus, the unknown impedance can be measured by adjusting the standard variable impedance till the bridge gets balanced and both impedances become equal. So this is the how we can measure the unknown impedance. So this unknown impedance can be measured. How this can be measured? By adjusting this standard variable known impedance till the bridge gets balanced. Once the bridge gets balanced, what will happen? Z1 is equal to Z2. So therefore, the value of Z1 is nothing but as Z2. So the value of Z1 which we have set, that is equal to Z2, because when Z1 is equal to Z2, then only the bridge gets balanced. So what is this point again? The value of unknown impedance can be measured by adjusting this standard variable impedance. Once you adjust this, so at some point this bridge gets balanced, and once the bridge gets balanced, what we have derived already, Z1 is equal to Z2. So that means the value that we have set at the series at the standard variable impedance is nothing but as unknown impedance. In this way, we can measure the unknown impedance. So once the bridges gets balanced, so the unknown impedance is nothing but as, once the bridges get balanced, the unknown impedance is nothing but as the impedance of Z1. So this is the one type of application of magic T which can be used for the measurement of unknown impedance. Thank you.